In this video we're going to be talking about power functions and end behavior models. Just to define what a power function is, a power function is any function in which you've got y equals a times x to the nth power, and in this case this is still a polynomial. We discussed polynomial functions in the most recent video. But a is a real number that is not equal to 0, so I'm using some shorthand here. And then n is a whole number. It's actually a natural number, but we'll just say it's a whole number greater than 0. Okay, so remember what made up a polynomial function was that n had to be a whole number, a had to be real, and n had to be whole. So now for a function to be a power function, n has to be a whole number, but has to be greater than 0. Okay, so just an example of some power functions. We have f of x equals 3x to the 4th power, so that's a power function of degree 4. We could have g of x equaling pi, since pi is a real number, pi times x, that is a power function. So, sorry, I have to sweep off some stuff off of my screen here. Let me get rid of that. And then let's just see how power functions work in terms of end behavior models. Okay, so a power function helps us because we understand the graph of a power function. Let's talk about that first. Okay, so y equals x squared will look like that. Y equals x squared. And then if we increase the number in front of the x squared, in other words, we increase the coefficient. If the coefficient is greater than 1, the function looks like that. So let's actually make that be let that be a g of x. Let's say that's equal to 3x squared. Okay, and then let's make an f of x out here that's a little bit wider. That wasn't a very good spot there. A little bit wider than our x squared. And that would be, let's say, h of x equaling, let's say, 1/2 x squared. So we can see what happens to the actual graph of our original function, x squared. It gets a little skinnier if the number in front of the x squared, if the coefficient is greater than 1. So greater than 1, it gets skinnier. And then if the number in front of the x squared, the coefficient, is less than 1, in other words, that coefficient there, a, is greater than 0 but less than 1, then it just makes the graph of x squared a little bit wider. But nevertheless, they all have the same vertex at 0, 0, and so they share that, and the general shape is the same. They're all parabolas. And then if we talk about the other one, in which it opens up down, that would be where there's a minus sign in front of the x squared. So let's say, let's let that be, yeah, we don't have an f of x yet. Let's let that be negative x squared. And then the same thing with a negative 2x squared, let's say, it would be more skinny, so skinnier than the regular negative x squared. So the negative x squared is like the normal width, and we have a skinnier and wider based on the coefficient of the x squared. So that takes care of kind of our power functions. They all are centered right there at 0, 0. And now, like I said, let's go ahead and see what happens with a power function and how that helps us graph other functions. Okay, let's do that on the next slide. Let's take another function that, let's say we look at y equals 5x squared minus 2x minus 1. Let's go ahead and change that to a plus 1. Okay, 5x squared minus 2x plus 1. And if we look at the graph of that, with just a little bit of effort, we can determine that the graph of that looks something like that. Okay, maybe a little bit more narrow, where it comes down and goes up. We've got a vertex right up here, somewhere in the first quadrant. Don't worry about where the vertex is. What I'm concerned with here is finding a model function to determine the ends of the graph. So if we were to zoom way out, okay, zooming way, 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 way out, we would see that the graph of this function looks something like this. Okay, again, we can't really tell, in other words, when we zoom way out, this little window here is not what we're concerned with. What we're concerned with is the ends of the graph. Like in function aerobics, these are what you can think about is that these ends of the graph are represented by your hands. Okay, so there's a hand there and there's a hand here. So you put your hands in the air when I say show me y equals x squared. Well, if I say show me y equals 5x squared, you would show me the same thing because the ends of the graph are not really going to change. And so what we want to do in this part of the video is talk about what would a good end behavior model be for the shape of this graph. Well, guess what? All you have to do is look right there. The end behavior model, we're going to use g of x to represent that, and the end behavior model is just that first term, or I shouldn't say the first term, but it is the first term when the terms are listed in decreasing order of their exponents. So decreasing powers. The highest power goes first, then the end behavior model will always be g of x, or whatever you want to call it, equal to the first term. Okay, and so we know that 5x squared looks just like this, and the ends of the graph are going to be almost identical, and what it would look like over here to the left would be something along the lines of this. So eventually, as x gets bigger in either the positive direction or the negative direction, away from the origin, the ends of the graph become very, very similar. Okay, and similar to maybe a concept that we've talked about before, where these terms are really insignificant for x values really big, positive or negative. And so we can act as if we're throwing them out, and we get an end behavior model, which we use models to represent something else, and that's what we're doing here. So like if you had a model airplane that was even a proportional to scale replica of the original real life size airplane, then you would have you have a model. You have a model that looks like that. Like architects build models for what they are originally or eventually going to build. Okay, so that's exactly what this is. We have a model that shows us what the graph is going to look like. So let's take a look at a couple more. Okay, now for this one, I want you to see if you've got the concept down. I'm going to give you an original function. Negative 3x to the third power minus 4x squared plus 5x plus 9. Okay? And I'm asking you, the question is, what would a good end behavior model be? In other words, what is this graph really going to look like? I'm not quite sure what I just said. I just got interrupted. I had to pause the video, so I'm just going to assume that I said, let's go ahead and make find an end behavior model that would describe what the shape of this graph would look like. Well, like I said, pick that first term. That's a polynomial function, and so we have an end behavior model. And let's figure out what that looks like. Okay, so what we remember, let me do this in black. What we remember about y equals x cubed is y equals x cubed looks like this, x cubed, just like that. Alright, so if that's y equals x cubed, then if we look at y equals negative x cubed, well, we know that that's a reflection. Okay, and what axis do we reflect that over? Well, in the case of y equals x cubed, it doesn't really matter which axis that you reflect the original graph over. As it turns out, whether you reflect it about the y-axis, like that, or the x-axis, like that, it still looks the same. So either way, you should know that you're supposed to reflect this graph of y equals x cubed about the x-axis. When the minus sign is on the outside, that's an up and down reflection, and an up and down reflection means that you're going to cross the x-axis. Okay, so I want you, though, to be really careful. Don't fall into the trap of those people that say, oh, all I'm going to do is I'm just going to look at that first term and I'm going to write it down right there. That's a good thing to remember, but you really need to know why that works, okay, so that you can apply this to other functions that don't always work that way. Okay, so y equals negative, let's get back to this part though, y equals negative 3x cubed would just be a little bit steeper, okay, a little bit steeper, but it would still go through the origin. Okay, remember, well actually you don't remember because I had a video but then something was wrong with it so I couldn't show you. I'll show you in class, but anyway, y equals negative x cubed, just a little bit steeper, or negative 3x cubed, negative 3x cubed, a little bit steeper. And again, this provides us with an end behavior model. We know that the model, that the original function, the one that we had with all four of these terms in it, is going to look like the shape of this graph here for large values of x, large positive or large negative. Okay, so that being said, what does the actual graph of this look like? Well, I would challenge you to get your calculator out and take a look, but or you can just watch me. Let me erase some of this stuff so I have a little bit more room to make it a little bit more clear. Okay, so we know what the graph of y equals negative 3x cubed looks like. Okay, and to get a little room to work with here, the original function actually looks something along the lines of this. It comes down here like this, goes up, and then it goes down like that. Okay, so that's the original function right there. Well, the graph of y equals negative 3x cubed we know is like this. It comes down and it goes out like that. And so, like I said, guys, the ends of the graph are what we're concerned with. As x gets big positive and as x gets big negative, we know what the shape of this function is. And so there you go. There's an end behavior model. Let me give you a couple problems to do on your own, which I don't think you'll need those, but I'm going to give them to you anyway. Just write these down. Y equals 4x to the fifth minus 2, and y equals 5x to the third plus 3x. Give me an end behavior model for each of these guys. Pause the video, and I'm just going to go right into it because it's going to take 2 seconds. That's a long 2 seconds, but nevertheless, those are your end behavior models for the two functions listed.